So hopefully you guys remember Wednesday's lecture, and we kind of talked about temperature scales and a little bit about the difference between temperature and heat. So for instance, we said, if you want to say, I want to stick a thermometer. This is my thermometer. This little thing, that's my thermometer there, and here's my thermometer here. So we're sticking a thermometer in these waters, okay? And you're like, the thermometer could read the same thing. Let's say 100 Fahrenheit. It's nice sort of bath to take, I think. So they're at the same temperature. So I'll say T1 is equal to T2. That's fine, okay? But if we were to say how much thermal energy those two objects have, the objects being water, can you see where thermal energy-wise the bathtub has a lot more thermal energy than the cup? Because M1 is M1 is significantly smaller than M2. Okay, M2 more thermal energy. And you'll hear me kind of go back and forth. We said thermal energy and heat are the same thing. So honestly, the thing we call heat, the bathtub's got it going on. Okay. So it's kind of hard to look, like it would be hard to take this table and say, that table, this will just take this top part, that has X amount of thermal energy. That's a kind of a tricky thing. But as we get going, we're going to say we can actually track its change in thermal energy, okay? But it's hard to see how much thermal energy it has. We would need to know the mass of this table. We would need to have a thermometer and measure the temperature of that table. And then we would also need to know something called the specific heat of that table. Now the specific heat, I'll just go ahead and say specific heat capacity, they're synonyms. I wished I wouldn't use the word table. I'm going to say you look this up. Look this up. Because it's in a table. Okay, you look up that value. You could say, what's the specific heat of plastic? You could Google that, and it would tell you what the specific heat of plastic is. So that's the third variable that you need to know if you're trying to nail down how much thermal energy something has. Its temperature, its mass, and its specific heat. Specific heat and specific heat capacity are the same. Okay. So when you find that value, like for plastic, when you find the specific heat for plastic on the internet, what they've done is, I just think this is so cool. Basically, they have taken 1 gram of plastic, 1 gram of plastic. This is supposed to be 3 dimensions here. And they have zapped it. This is my little zapping. They have zapped it with energy, basically heat energy, in order to get the temperature to go from, in order to get the temperature to go from, we'll go 14.5 degrees Celsius to 15.5 degrees Celsius. Okay? That change there is 1.0 degrees Celsius. That makes sense? Okay. So basically they zapped it 1 gram with amount of energy to make it go up 1 degree Celsius. That's it. So specific heat or specific heat capacity has a symbol, and it's not SH. It's capital C with a little p there. I don't know why. I'm not sure why. Units, and you might get this from kind of the little box that I drew, what specific heat means. Okay, units are energy, we zapped it with. Energy, joules is a great unit of energy. We talked about that on Wednesday. Energy per gram, because we zapped 1 gram, per degree Celsius, because it budged 1 degree Celsius. Okay, those are the units. Joules per gram, degree Celsius. Now, with that said, This one over here, this one is my least favorite way to express specific heat. Joules per gram per degree Celsius. I'm like, what does that mean? So I understand that sometimes you're not wanting to, but I don't like it. I would rather, and I don't have it up here, but what makes more sense to me right now anyway, is to go joules per, and then begin quantity, grams times degrees Celsius. I would prefer that actually. That makes more sense to me. Okay. Right, so specific heat, you look it up. It's the third quantity in order, and it's specific heat is specific to a substance. Okay, water has a specific heat, plastic has a specific heat, air has a specific heat, concrete has a specific heat. So if we go back to kind of that little box that I drew and put 1 gram on it, zap it, in order for it to change from 14.5 degrees Celsius to 15.5 degrees Celsius, 1 degree Celsius change, remember we talked about this on Wednesday, that the Celsius scale is the same units as the Kelvin scale. So if you change 1 degree Celsius, and in Kelvin, in absolute temperature scale, we don't use the word degree for some reason. We change 1 degree Celsius, you change 1 Kelvin unit. Okay? So. All right. So these are actually just a list of specific heats of some substances. So when you work problems, you might need to refer to the specific heat of a substance. Yes?
Do we have to memorize any of them?
The only one you need to memorize, see it's up there, no, these are elements, is water, and it's coming up in a minute. No, you don't need to memorize them. I will say sometimes the problem with these problems that we're going to do in thermodynamics is they take on different twists. Sometimes the twist is to come up with a specific heat with given information, but to calculate it. So the one you need to memorize, yeah, there it is. Oops. I'll go ahead and do an arrow here. This one right here. Water. But one of the things we're going to, in this unit, talk about is that if water is in its liquid state, it will have a different specific heat than if water in its gaseous state or its solid state. So the specific heat of water in its liquid state, yep, I think you should memorize that, is 4.184 joules per gram degrees Celsius. That's the specific heat kind of with unpacked units. And I don't know if you remember, you're like 4.184. I know we talked about that on Wednesday. And here's where we talked about it. We said that, let's see, how's this go? By definition, 1 calorie is equal to 4.184 joules. And we said that is actually exact. So that's where that 4.184 comes from. So in other words, the specific heat of liquid water would be what? 1.000 calories per gram degrees Celsius. Oh, and do you notice? I'm surprised no one caught me on this. Okay, so look at the units up here. So I'm actually okay. Okay, and it goes to this idea of it's a change in temperature, and the steps in the Celsius scale is equal to the steps in the Kelvin scale. 1 step in a unit, Kelvin unit is equal to 1 step in the Celsius temperature scale. So actually we're fine. I know that might, but that's right, actually. Okay. All right, here's some more specific heats of some substances. So, yeah, you can see actually the 3 phases of water. And the only one I would hold you to is the liquid phase, the specific heat. But here, we've got all 3. Okay, so if it's solid, the specific heat, specific heat capacity, it's kind of, I say it's kind of how stubborn it is to heat up and cool down. When it, not change phase, but heat up and cool down as it's an ice. Heat up and cool down as it's liquid. Heat up and cool down as it's a vapor. Okay? Oh yeah, see, so I did have an arrow for that one. And does this make sense? Actually, if you look at, just kind of glance at the numbers, 4.184 joules per gram degree Celsius, that's pretty high. Okay, what does that mean? It means you have to pump 1 gram of water with a lot of joules of energy in order for it to increase its temperature. That means it's very stubborn to heat up and very stubborn to cool down. I'm kind of pointing over here to Joshua because when in meteorology we talk about that, you know, the whole phenomenon
Latent
of,
heat.
yeah, well, latent heat is changing phases, but this is just this is why your swimming pool takes forever to heat up in the springtime. Okay. So I'm like, well, what's up with this other column? So the difference between these two columns, one is joules per gram degree Celsius, and the other one is joules per mole degree Celsius for Kelvin. You know what I mean. It's the same thing. Okay. So one of the things that I don't like up here, like how they did this, look at this. I hate to complain about my slides, but, you know, to me, this doesn't look like it's in the denominator, but it is. You know, this is joules per gram Kelvin. And this is joules per mole Kelvin. By golly, you could go back and forth between those two just by the molar mass of the compound or by the element. So, all right, so let's kind of, these aren't really a problem. This is just to kind of get you thinking. So we have two metals. We have copper. Okay, the specific heat of copper is 3.85. We have another element, aluminum, and aluminum, the specific heat is 0.897. So both of those are joules per gram degree Celsius. So does this make sense? Aluminum is more stubborn to heat up and cool down. And this little thought problem is just saying we're going to zap both of them with 500 joules of energy. And they have the same masses. Okay. So does this make sense that with regard to their final temperature, the one that is more stubborn to heat up, we're zapping it with the same amount of energy, but its final temperature is going to be less. Okay, the one with the lower specific heat goes ahead and I think of it as kind of responds to the energy that you added to it, heats it up more to a higher final temperature. I'm not talking about speed here, just to a higher final temperature. Okay, so we're going to kind of mix it up here. Again, we have copper with the lower specific heat on top, aluminum with the higher specific heat down on bottom. Now, in this case, energy is the variable. We want to have the same final temperature. What is this, a 30-degree temperature swing? 32 degrees, 30 degrees. We want the same temperature change, the same masses, okay? But does this make sense? How many people think, I'll just go ahead and put it up there. We have to zap the aluminum with a lot more energy in order to make that happen. So in order to get the same 30-degree temperature swing, we have to zap aluminum with 673 joules versus only 289 joules for the copper. Now, you see the variable Q, and I'll explain Q here in a minute, but Q actually is just a change in thermal energy. So I haven't said what that is yet. I think I am right. Coming up. Okay. So this goes back to what Shelby asked. Do you need to memorize any specific heats? And it's like, you guys need to memorize the density for water, so no, why not the specific heat for water? Okay, so the density and the specific heat for water. Specific heat for water, we said was, and again, don't let the whole J/G/K screw you up. 4.184 joules per gram. We'll go with Kelvin. I'm fine with that. Same as Celsius. Okay. So there's our Q that we saw a little bit ago. We needed to, we used it for zapping that was like the energy input a little bit ago. But what Q means is energy added or energy given off. Energy change, and it's in units of joules. So I don't do a lot with formulas in here. There are some formulas, I guess, in general chemistry. Okay, so M is mass. C sub P, specific heat. We haven't done a delta yet, I don't think. Anytime you see the triangle, that actually is the Greek letter delta. I think it's a lowercase. So that is delta. So sometimes they'll call this delta T, and it means, anytime you see delta, that means change in. So change in T, change in temperature. Okay, so we started out this by the whole bathtub thing. If you have a cup of water or a bathtub full of water, which one has more energy? We said thermal energy, heat. We said the bathtub because it has more mass. So we have up here the mass, okay, the specific heat, and we're going to track not the absolute heat, but the change in heat. Okay. So Q doesn't have a delta there, but it's kind of delta-ish. Change in thermal energy, that's what Q is, and of course delta T is change in temperature. So we're all about at least dimensional analysis. Dimensional analysis means making sure your units work. So I'm going to kind of just slip up here, and I'm going to say, I'm going to plug in a unit for unit for mass. I'm going to put grams. I'll put grams over 1. Unit for specific heat is, I'll go ahead and put joules per gram degrees Celsius. And unit for delta T, I'm going to go ahead and put degrees Celsius over 1. So I just love the whole unit thing, because if we let units cancel, of course our grams cancel, our degrees Celsius cancel, and we're left with units of joules, which as it turns out is the units for Q. So even though we're using like an equation sort of thing, and you can rearrange it and plug in, kind of like we do in physics, that's fine, and I encourage you to do that. You just have to carry the units along for the ride, and they will give you the right. They'll either show you you were wrong or right in rearranging your equation. Okay, so delta T, change in temperature. Deltas are, and we'll be talking about more deltas, changes in physical quantities. Deltas are always what the final state was minus what the initial state was. So change in temperature. So a little bit ago, I said you're going to the specific heats are kind of like, think of them taking a gram of substance, zapping it with energy to get it to go from, what did I say, 14.5 degrees Celsius to 15.5 degrees Celsius. Okay, so our final temperature was 15.5. Our initial temperature was 14.5. And these do carry a sign. So, of course, when we do that, we get, what? 1.0 degrees Celsius. That's our delta T. So delta T's sign makes a difference. The one that I was showing you where we zapped 1 gram and it went from 14.5 to 15.5. Did I do that right? Okay. I don't know. I'm not sure. I'd have to go back and listen to myself. But, yeah, I did it right because it went from 14.5 to 15.5, yes. So in that case where we were zapping it, okay, we got a positive delta T. we're actually going to look for when objects are cooling down. And in that case, your final temperature is less than your initial temperature. So can you see where you're going to have a negative delta T? Okay. So, oops. This one is your positive delta T. And this one is your negative delta, or doesn't say. It is. There it is. One more build. And this one is your negative. And I'm all about kind of picturing things. I draw a lot of pictures when it comes to working these problems. And so bottom line is this one, you are adding energy. And this one, energy is oozing out. Or you could say energy is released, E released. And on Wednesday, we're going to talk about released into what. But okay. So did I have this slide twice, or is this just kind of a, oh, did I have it before too? This is the second time this slide? Okay, but all this slide is saying is what I've been saying. When I hold this up, okay, that's my temperature leap. On the Celsius scale, my temperature leap is the same as the temperature leap on the Kelvin scale. That's it. Okay. So if I write up that Q, and that seems like a rap song, Q is equal to M C sub P delta T. I know. Okay. So if you look at mass, mass has to be positive. Specific heat is always positive. Okay. So the only thing you have that can be positive or negative is the delta T. So what this is saying is whatever sign this is, it governs what your Q value sign is.
Now that you're a rapper, you have to come up with a name.
Right. Oh my goodness, I don't think so. Well, they'd go that route. Okay. So a little bit ago, I told you if your delta T is positive, then energy is added. If your delta T is positive, your Q is positive, energy is added. Okay? If your delta T is negative, less than 0, if your delta T is negative, that makes your Q negative. And I said that's associated with something not taking in energy, but something giving up energy. I'm going to go ahead and add a couple terms. I think I've introduced these terms earlier in the course. I don't remember. But do you remember I talked about endothermic? I'll go ahead and put endothermic on the top one, and I'll put exothermic on the bottom one. We'll see if that helps. And then I always think of this over here, positive, negative. Saying the same thing, but in thermodynamic problems, if you can kind of remember that, and actually not, there's other areas of chemistry where this positive and negative and exothermic and endothermic and exothermic come in. Okay, so let's do a problem. So what I would do if I was working this problem is draw my little beaker. I draw some water, and then I would take these variables and I would take those numbers and give them variables. So on the next slide, actually, you're going to see that M of water is equal to 37.7 grams. T sub I, initial temperature, is 52.0 degrees Celsius. Final temperature, T sub F, is 5.2 degrees Celsius. Cool. And then do you guys remember the specific heat of water?
4.185.
Close. 184. 4.184. Yep. Joules per gram degrees Celsius. Now, I knew to pull all those numbers because I'd read the problem at my desk before coming to class. But even if you didn't know, sometimes if you're like, I hate word problems, you might try this, just taking them kind of number by number and pulling them out and saying what they are. Okay, so it's cooling down, so energy's given off, so we should have, what, a negative Q. Does that seem right? Energy given off? I'm thinking so. So is the water losing energy or gaining energy? How many people think it's losing energy? Me too. Can't remember how my slides go, but it is losing energy because it's cooling down. The next question, what is the energy change of the water? Energy change is Q. So bottom line, all I need to do is Q is equal to MC sub P delta T. Okay, so that's actually how we're going to work this, where Q is the energy change. All right, here we go. So this slide just kind of pulls out what I pulled out before. The mass was given, the specific heat you need to memorize. Again, don't let those units throw you off. Units of mass and temperature are in the bottom. Then you have to show everything. You know how you guys have been good calculating your molar masses of compounds? You also need to show your delta T's. You have to show that because it's part of this. You're like, why do I need to show this? I mean, I can do this in my head. Well, two reasons. One is because I said so, and the other is it could save your butt on a test. Because if you just have a brain fart, then I can see that, well, that was your delta T. So deltas are always, changes are always final minus initial. In this case, the final was 5.2, and the initial was 52.0. We're subtracting, so we round according to decimals, okay? And don't lose the sign. So it is negative 46.8 degrees Celsius. All right. Now we're ready to plug in. Yay. Q is equal to M, so 37.7 grams. I put it over 1 because I love to see those units cancel, and that makes it best. C sub P is that 4.184 joules over grams degrees Celsius. And that delta T we came up with was that negative 46.8 degrees Celsius. So grams cancel, degrees Celsius cancel, and we're left with units of joules. It looks like we need to round according to 3 significant figures. So 3 significant figures. Now, would you have to put this in scientific notation? No. In fact, if I was doing this and I didn't, I might not worry about it. So negative 7,380 joules, or negative 7.38 times 10 to the third joules, the same thing. Now, a lot of times we want you, and I don't think it asked this time, to take those energy units from joules to kilojoules. And that's the last thing I'm going to show you. So that last step there, you probably wouldn't have to do, because I don't think it said, just said how much energy, what's the energy change. So to convert from joules to kilojoules, we take negative 7,380 joules over 1 times 1 kilojoule over 1,000 joules. And we get negative 7.38 kilojoules. No, you can't just move the decimal place over 3 places. As tempting as it is. So kind of watch for that. It's kind of like in your titration problems, you had to make sure if it wanted volume in milliliters or leave it liters. Okay, it's kind of a similar thing. So that was the energy, and I just think it's so cool. It's like invisible energy. That's little strokes of energy released as that cooled down. So a little bit about semantics. We would say Q is equal to negative 7.38 kilojoules. The change in thermal energy is negative 7.38 kilojoules. Or we could say, we could actually imply the sign of negative in a text, in context. We could say that 7.38 kilojoules of energy was lost or released. So we could do either one of those. But you probably wouldn't mix and match the two. You probably would not insert a negative sign and say negative 7.38 kilojoules of energy was lost. If you want to look like you really know what you're talking about. So. Okay, so this is where I brought these two problems forward just because I care. So let's take a quick look. So 7.1 and 7.2 are on the last slide, and these will be due on Wednesday, which will be here before we know it. Okay, so the first one, actually there's two parts to both of them. You're supposed to calculate Q, the quantity of heat, in kilojoules. Okay, in the first case, you are raising a certain volume of water from 22 to 29.4 degrees Celsius. So I'll push these out there, but all it is this is what it looks like. We're going to use Q, and actually in green here I said for mass you're going to have to use that volume of 9.25 liters and the density of water, okay, to get the mass. But other than that, it should be kind of straightforward. For B, you're dealing with a piece of aluminum bar, and the mass is given, the change in temperature is given. Now you might have to read it a few times, because when I was looking at my office I'm like, wait a minute, there's only one temperature given. But notice that is delta T. It says calculate the quantity of heat in kilojoules associated with 33.5 degree decrease in temperature. Cooling down. Okay, so that would be, we cited a negative delta T. Anyway, and then the next one, next two look like this. Calculate the final temperature. Now this is a good thing to get in the habit of. So the first one says calculate the final temperature if you are going to zap this water with 875 joules of energy, the mass of the water is given, and the initial temperature of the water is given. So what I would do is basically, you know Q, you know M, you know specific heat of water, okay? You don't know delta T. I would get delta T first, and then recognize that delta T is final minus initial, and you know initial, you don't know final. That's it. That's a good one to do. And then the other one deals with a block of platinum. The specific heat of platinum is given. Again, you're after what's the final temperature, and in this case, you're going to zap it with 1.05 kilocalorie of heat. So we deal with joules. Calories, of course, are those pesky English units. So the specific heat is given not in joules per gram degree Celsius, but in calories per gram degree Celsius for your convenience. Okay, so, but again, you can rearrange this. Okay, you know Q, you know M, you know specific heat, you don't know delta T. I would out and out find delta T first, and then I would, after I have delta T, say, well, I know my initial temperature, but I don't know my final. That's how I would do it. I know you could just do it in one equation, but I kind of prefer it that way. Okay, that's it, man.